The central processing unit, also called the CPU, is the centerpiece of every computer hardware architecture. It is the hub of computation, if you will, because this is where all the calculations of the machine take place. And it is also the seat of control. This is where decisions are made about which instruction should be fetched and executed next. In this unit, we're going to talk about the HEC CPU, the specification of the CPU, and how we actually are going to build it. Now, as usual, it always pays off to start with the abstraction. So we can think about the HEC CPU as some sort of a black box magic that performs two truly remarkable things. First of all, well, it's a 16-bit processor like the entire computer. And the first thing that it can do is, given a certain instruction written in the HEC language, it will execute this instruction. Now, this is something which, in my opinion, is truly remarkable and dramatic. Because up until this point, when we wrote programs, the programs existed on a piece of paper. They were completely static. They were simply a bunch of symbols that describe some fantasy of the programmer who wants to actually make something happen. But now we can actually take these programs and put it into a machine that turns them into reality. The programs become music that you can listen to, or video clips that you can watch, or some airline reservation system, or whatever. So the CPU is this very unique and special agent that takes this program specification and turns it into a reality. And if this were not enough in its own right, the CPU can also do something not less remarkable. In the process of executing the current instruction, it also figures out somehow which instruction should be executed next in the program which is currently running. And of course, since we talk about the HEC computer, we assume that all these programs are written in the HEC machine language that we studied or looked at in week 4. So given that this is the CPU abstraction, the next thing that I'd like to discuss is the more detailed specification of this apparatus. Well, the first thing that we have to remember is that the CPU does not work in isolation. It is connected to other devices inside the computer. In particular, in this particular HEC architecture, the CPU is connected both to the instruction memory and to the data memory. With that in mind, here is the specific input and output connections of the CPU. And let us begin to review them from left to right and from top to bottom. So first of all, we have 3 inputs coming from 3 completely different sources. First of all, there is the 16-bit data value, which is the value of the currently selected data memory register. This is the value that the CPU is going to operate on. Now, what exactly do we want the CPU to do? Well, the next input, which we decided to call instruction, which is a very sensible name, describes a 16-bit input, which is the value of the selected instruction memory register. And remember that at any given point of time, there is always a selected register in the instruction memory, and there is always a selected memory register in the data memory. So always something comes into the CPU. The third input, which we decided to call reset, is a 1-bit input, which I will discuss later in this unit. On the right-hand side, we see the outputs of the ALU. So first of all, if the ALU wants to write something to the data memory, it has to specify 3 different things. Number 1, what is it that we want to write? And this is stored in or emitted through an output called out_m. Number 2, where do we want to write it? We have to provide an address, and this is the job of the next data output. And the third output is a load bit that enables the data memory for write operations. So these are the 3 data outputs, if you will, of the CPU. In addition, there is one extremely important output, which we decided to call PC for reasons that will become clear in a few minutes. And this output holds by some sort of magic, the address of the next instruction that has to be fetched and executed in the next cycle of this computer. So, how do we implement this magic? How do we make all these good things actually happen? Well, here is one way of doing it. This is our proposed implementation of the functionality that we just described. It is not the only way to build a CPU, but this is a pretty good one because it's very elegant and simple and relatively easy to do. So, before we get into the actual details of this architecture, let us look at the interface. If we look at the interface of this hardware diagram, we see that it is 100% identical to what we saw before. We have 3 inputs coming in, and we have 4 outputs coming out. And given that we made this observation, we can now delve into the details of the actual architecture. Another important thing that we have to look at before we begin to understand what is going on here is that within this architecture we have many labels labeled by the catch-all symbol C, which I use to represent the notion of control bits. So in order to make all these chips work together, the designer of the CPU has to make sure that different bits, different control bits arrive to the right locations, and these multiple messages together will cause the CPU to do what it's supposed to be doing. Now, if you look at this architecture, after the first minute or two of bewilderment, you will realize that everything here is extremely standard. You see the ALU, which you built in Project 2. We see 3 registers, which we call A, D, and PC. And these registers are identicals to chips that you built in Project 3. And we see 2 muxes, which we built in week 1 of the course, in Project 1. And therefore, putting together this architecture is just a matter of assembling chip parts that you've already built in previous weeks in this course. Another thing that you see in this diagram is all these C labels, which indicate control bits that go into various locations in various chips. Now, we have intentionally left those, the specification of these control bits somewhat opaque, because we want you to figure out how to actually piece all these things together. And we will have much more to say about it in the unit that discusses how we actually build this architecture. Now, before we build it, we have to describe what this architecture actually does. And in doing so, I find it kind of interesting to think about this architecture as an orchestra that works together, many different instruments, in order to produce some great symphony, and the symphony is the execution of the current program. Just like a regular orchestra, it can play many different pieces of music, and the current program determines what it actually executes. So I would like, in the remainder of this unit, to focus on different sections in this architecture, and let us begin with this section that deals with the current instruction. So zooming in on this section, we see that it consists mainly of a register called A and an instruction input that connects to this register through a multiplexer. And here is an A instruction arriving to the machine in the current cycle or some cycle. And here is also the symbolic mnemonic of the same instruction, which is easier to read, but obviously the computer doesn't care about it at all. This is just for communications between me and you. So we see that this instruction seeks to load the value 3001 into the A register, and of course to do everything in binary. So in order to carry out this instruction, the CPU has to do several things. First of all, it has to decode the instruction. It has to take this 16-bit value and separate it into an opcode and a 15-bit address, or a 15-bit value. By the way, how do we know that it's an A instruction? Well, we can look at the opcode. The opcode is 0, and according to the hack machine language specification, it means that it's an A instruction. So the CPU says, aha, I know what to do with it. I have to take the next 15-bit value and put it inside the A register. And notice that this is exactly what the gate diagram does. The 16-bit values go through the register. and into the register. Another thing that the CPU does, and we cannot see it in this diagram in order to avoid clutter, but this is something very simple. It takes the output of the A register and emits it outside the CPU via the output, which we called, I think, address M or M address. You can look it up in the overall architecture of the computer. So this is how the CPU handles an A instruction. Now, the next thing that we're going to look at is how the CPU handles a C instruction, because after all, in this hack machine language, we have two generic instruction types, an A instruction and a C instruction. So we have to be able to entertain and handle any one of these instructions. Well, the C instruction, like the A instruction, consists of different fields. And the first field is the opcode, which happens to be 1. This is how the CPU can tell that this is a C instruction. But in addition to this, we have several other fields, and we can see them more clearly if we look at the symbolic manifestation of the same instruction. Now notice that I'm using color coding to associate the bits with the symbolic mnemonics, but these colors obviously are completely meaningless for the computer. They are just a way for us to communicate more easily in the course. So how does the CPU handle with such an instruction? Well, you may have guessed the first thing that has to be done is to decode the instruction. So the ALU takes this 16-bit value and it decodes it into 4 different fields. And these fields will later on be used in order to power up and manipulate different elements inside the computer architecture. What we discussed so far was how the CPU handles the A instruction, but if you look at the gate diagram, you see that the same A register can be also fed not necessarily from the instruction input, but rather from the ALU output. So we have to decide. In some cases, we want the A register to be fed from the instruction, and in other cases, we want the ALU to be fed from the ALU output. Now, you may have guessed how we do it. We know that in different situations, we deal with 2 different instructions. In some cases, it's an A instruction with an opcode of 0, and in this case, we want the input to come from the instruction. In other cases, it's a C instruction with an opcode of 1, and in this case, we want to route the input of the A register in such a way that the input will come from the ALU. So it is the job of the CPU designer to inspect the opcode of the incoming instruction and decide from which source the A register will take its next contents, so to speak. All right, so this is roughly how the CPU handles incoming instructions. And let's go back to the overall architecture and focus on the next section that I'd like to discuss, which is the operation of the ALU, which is by far the most complex part of this architecture. All right, now we see here this segment that deals with the ALU, and we see a C instruction coming in instead of the A instruction that we saw before. And let us remember that the C instruction consists of different fields of bits, each one of which means something else. And another thing that we have to remember is that the ALU is a combinational chip. It always computes something. There's always some inputs coming in, and there's always some output coming out. And when you look at the diagram, you see that the inputs of the ALU come from 2 different sources. One of them is the D register, the current value of the D register, and the other one is either the value of the A register or the value of the selected memory register. And there's a multiplexer that takes care of this decision of where to take the value from. And the control bit of this multiplexer is one of the bits in the instruction. So once again, the CPU designer has to take care to take this bit that determines from which we want to read the input of the ALU, and the ALU will then get the correct inputs or the inputs that the programmer intended it to receive. So we have the inputs lodged in the input pins of the ALU, and the ALU goes to work, and how does it know what to do? Well, the ALU also has 6 control bits that basically taken together tell or specify the ALU which operation we want to carry out. Now these bits are taken from the instruction, and I'm using some color coding here to help distinguish which bits go where, but of course these colors are completely meaningless as far as the computer is concerned, and I'm using them only for didactic purposes. So the CPU designer has to take these 6 green bits, or more accurately copies of these bits, and route them all the way to the control bits of the ALU. So now that we have all this information, we have the input data, we have the operation that we have to carry out, we can the ALU can actually compute something, and out comes the ALU output. Now, inspecting the diagram, we see that the ALU output is simultaneously fed into 3 different destinations. The first destination is the D register. The second destination is the A register, and it goes through a multiplexer. And the final destination is outside the interface of the chip, so to speak. So the same ALU is fanned out into 3 different places, and so we have the situation that we have the same ALU output knocking on 3 different doors. But the fact that it knocks on these doors does not necessarily mean that the doors are going to open. We have to decide, or the programmer has to decide, which door has to be opened. This decision is made by the next field of bits that I want to focus on, and these are called, in our jargon, we call them destination bits. We have 3 destination bits, and these bits determine whether or not to open the D register, the A register, and the data memory to accept the ALU output. So if, for example, the green bits would have been 0, 0, 0, then it's very nice that the ALU computes something, but this value will be lost. No container in this computer will be open for business, so to speak. And if we set these green bits to 1, 1, 1, then all of these containers will receive the same output simultaneously. So we can play with these bits as we've done in week 4 when we wrote programs. Although we did it in assembly and in symbolic way, we can do it with machine language. And once again, we have a way to program this architecture so that the ALU output will be selectively absorbed by different locations in this architecture. All right, moving along. Another thing that we have to remember is that the ALU also computes and outputs 2 control outputs, which I think we call the ZR and NG. And these 2 control bits document whether or not the ALU output is negative or 0. And these 2 outputs play a key role in what will be described next, which is the control logic of the CPU. But before we talk about this logic, I want to, as promised, I want to say a few words about the reset input that we see coming into the diagram from the left-hand side at the bottom of the slide. And of course, when you build a chip, all these sides, up, down, left, right, mean absolutely nothing, but it's useful to communicate about it when we talk about gate diagrams. So let us say a few words about this reset bit, and in order to do it, we have to try to envision how the heck computer will look like if we actually set out to build it. Well, it will be a black box, and as you see, this black box is equipped with a single push-down button, and this push-down button is called reset in our jargon. And the idea is the following. This black box, the heck computer, is already loaded with some program written in the heck machine language. And up until now, it does nothing. The program is inside, but nothing is happening. Well, if you take your finger and push this reset button in and let go, what will happen is that the computer will start running the current program. Well, you look at whatever comes out of this computer, and in a few minutes you will see that we can attach a screen to it and a keyboard. You look at the program's execution, and at some point you decide to reset the computer or rerun the same program again. You take your finger, you push it inside the reset button, you let go, And by doing this, the computer will restart running the same program again. Okay, so this is the kind of behavior that we want to implement in the control logic of the CPU, among other things. All right, so now that we understand how the reset button works from the outside of the computer, so to speak, let's go back to the CPU logic and explore the control logic of the CPU. Well, it doesn't make sense to talk about control if we don't have some instruction that gives meaning to the control operation. So here is an example of a C instruction, and it's a schematic instruction. It's not zeros and ones, but I used some mnemonics to, and also color coding, which is completely meaningless as far as the computer goes. I used these mnemonics and colors in order to emphasize that we have here different fields of bits. Each field is designed to do something else in the overall computer architecture. And when we talk about control, I want you to focus on these 3 bits, which we call the jump bits. If you recall, if the 3 jump bits are 0, it represents a no jump situation. If the 3 jump bits are 1, it represents unconditional goto. And any other combinations of zeros and ones in the jump bits represents a conditional goto. What I've just said is part of the heck machine language specification. And now it's the job of the CPU to turn this specification into reality, to realize this abstraction. So how do we do it? Well, the hero of our story is a humble register called program counter. It's actually a counter. And the program counter is also called PC in our jargon. And in what follows, we want to focus on what happens inside the PC. So here is the desired operation of a typical program counter. First of all, and foremost, the one thing that we want the program counter to do is to always emit the address of the next instruction that has to be executed. So let's keep this in mind. Now, if you want to start or restart the computer, well, in this case, we have to set PC to 0 because we want to execute the first instruction in the program. So PC equals 0 makes a lot of sense. Otherwise, if we have a no jump situation, if the current instruction is such that the 3 J bits are 0, then we want the program counter to increment by 1 step, so that the next instruction that we will execute will be instruction number 1, and then instruction number 2, and 3, and 4, and so on, as long as we don't have a jump. However, if the current instruction is such that all the J bits are 1, then we have we have an unconditional goto. And in the case of an unconditional goto, we want to set the PC to A. Why? Because if the programmer knows what he's doing, then the programmer has already taken care to enter the address that we want to jump to the A register. So if we do PC equals A, PC, the program counter, will emit the address of the next instruction that has to be executed. And finally, if only some of the J bits are 1, 1 or 2 of the J bits are 1, then we have a conditional goto. If we have a conditional goto, we have to look at the ALU output and decide if this goto should actually materialize. That's the whole idea of conditional. We have to check if the condition is true or false. If the condition is true, then we want to make a jump. Otherwise, we want to ignore the goto and just do PC++. So I hope that you are convinced that this abstraction makes sense. That's exactly how a program counter has to work in every computer. And what remains to be seen is how do we actually make it happen? Well, the answer is already on the screen here in front of you. The logic architecture is such that the PC will do exactly what we want it to do. And let us convince ourselves that this is indeed the case. Well, let's look at the reset input. And remember that in order to start the computer, in order to cause the computer to start executing the current program, we push the reset button in and we let go. So if the register is 1, we want to set PC to 0. Otherwise, we have to look at the current instruction. And the current instruction may or may not have jump bits. If the jump bits are, well, given any combination of jump bits, all the way from 000 to 111 and all the possible 8 combinations of three jump bits, given every one of these combinations, we have to look at the jump bits and simultaneously look at the ALU output and decide if we really want to carry out the jump. So in the slide, I described this decision as a function, this F function, which I made up, completely meaningless in the computer architecture, but I'm using this symbol F to try to say that we look at these two different pieces of data together, we combine somehow this information, and we make a decision. Do we want to jump or not? I store the result of this decision in the symbol load. And if you look at the diagram, you see that this load is actually the load bit of the program counter. So if load ends up being 1, yes, we want to jump. So we do PC equals A. PC equals the current value of the A register, which contains the address to which we want to jump. Otherwise, we do PC++. At the end of all this operation, and when all the dust clears, what we'll get is that the PC always emits the address of the next instruction that has to be fetched and executed. This pretty much wraps up the description of the CPU implementation, and the only thing that remains to do is to actually build it. But before we set out to build it, we have to remember that all this complexity is just one element in the overall computer architecture. That said, it is by far the most complex and interesting element in the architecture, and we are going to build it, not now, but after the next unit, because in the next unit we'll describe the overall architecture of the hack computer, and then we'll get our hands dirty and actually set out to build both the CPU and the entire hack computer.